In this section, we will see what is IPSLA, why do we need it, the process of using IPSLA, and the commands for configuring and verifying IPSLA. Cisco officially defines IPSLA as sending synthetic probes across the network simulating real network traffic to collect in real time measurements of performance between multiple network locations or across multiple network paths. So what does this really mean? This means that we are going to create these artificial packets that we are going to call probes. We are going to send them to destinations, and then we are going to wait for these destinations to reply back. And then after receiving these replies, we are going to start gathering statistics. So what are these statistics that we are going to gather? We can tell whether a remote device is reachable or not. We can tell what is the round trip time in order to maintain communication with a remote device. We can calculate jitter, delay, packet loss, out of sequence packets for a destination or per hop. This is useful for real-time applications such as voice over IP or video conferencing. We can estimate the amount of time that we are going to take to establish a TCP connection with a remote part of the network. We can also gather HTTP download times, FTP download times, DHCP as IP assignation times, and many others. So why do we need IPSLA? Maybe we need to abide by a customer contract where we need to do measurement, monitoring, and verifying of this customer service level agreement. Maybe we need real-time network performance data. Maybe we need to perform network health assessments or troubleshooting or problem analysis, or maybe design better network topologies. Just a quick note here, Cisco IPSLA technology is not the only one out there. Other vendors have their own probes technologies. For instance, Huawei has NQA, Juniper has RPM. In order to use IPSLAs, we need to follow this process. First, we have to configure the IPSLA. Optionally, we have to configure a responder. Then we are going to schedule it. Then information is going to start being created. The most recent results are always available. All the results can get stored in history databases that are based on buckets. These are viewable through the command line interface or by pulling through a network management system. So let's focus on the first step, how to configure IPSLA settings. First setting, disabling the IPSLA control protocol. With the parameter disable control, we are going to disable using the IPSLA control protocol, which is enabled by default. This protocol is only used when the destination is a Cisco responder, so if we are not using a responder, it is recommended to disable this protocol to avoid creating confusion at the destination. Let's talk now about the timing settings for IPSLAs. Once we start sending probes to a destination, we are going to repeat this operation all over again and all over again. The interval that we are going to wait before restarting an operation is known as the frequency. By default, we are going to repeat it every 60 seconds, but we can change that. The next timing parameter is the timeout. It represents how much time are you willing to wait for a response to come back. Since we cannot wait forever because we have to restart the operation given the frequency parameter that we just talked about, timeout responses are ignored. By default, it is 5,000 milliseconds, but we can change it. The next timing parameter is the threshold, which is the time after a returning packet is still accepted, but it is flagged as above threshold. It represents an ideal limit that we want to set for our network. If we start receiving packets after the threshold, that means that our network is not behaving as expected. By default, it is 5,000 milliseconds, but we can change it. These timing settings must follow the following rule. The frequency must be greater or equal than the timeout, and the timeout must be greater or equal than the threshold. Now let's see how to configure the statistics for a given IPSLA. There are several ways to store and show statistical information for our probes. We can do aggregated, snapshot, history, or frequency distribution statistics. I'm not going to go into detail of each one of these, but for instance, for aggregated statistics, these statistics corresponds to 2 hours of information. We can change that, for instance. We can also customize the probes, packet headers, and payload. The destination IP and the destination ports are mandatory parameters. However, we can customize the TOS fields, the source field, and the payload. The next step in the IPSLA process is optionally configuring a responder. A responder is a Cisco iOS component that listens to IP SLA probes and generates a response. Depending on the IP SLA probe, it may be required, optional and recommended, or not required at all. The most important fact about responders is that responders use the IP SLA control protocol. So what are the advantages of the IP SLA control protocol? With this protocol, responders can dynamically learn to what UDP or TCP ports they should listen to for incoming probes. This reduces the amount of configuration because all of this is dynamic on the responder side. We will have security between sender and responder with MD5, and we will have better time calculations because we are going to use timestamps. The packet arrival and packet leaving timestamps. This means that, in other words, we are going to avoid the processing delay issue. So what is the processing delay issue? The processing delay issue stems from the fact that we cannot know what is the time that a device takes since it receives a probe until it sends a response back. Since we need to know only the network delay, we are including this unknown processing delay within our network delay measurements. Just a final note on these destination devices that are not responders. We have to make sure that this destination device supports certain RFCs depending on the probe. For instance, for UDP probes, this destination device must support the RFC 862 UDP echo, and for certain ICMP probes, these destination devices must support a full implementation of the ICMP RFC 792. This is a little chart that summarizes what happens when we use a responder as destination device and what happens when we use any other device. In order to configure an iOS device as responder, we will need this command. This is the most important command for responder, and we can set up to what ports a responder is going to listen to with this other command. Let's talk now about scheduling IPSLAs. The first scheduling parameter will be the start time. By default, IPSLAs don't have a start time. We need to provide one, for instance, now, sometime after now, a random time after now, and so on. Once started, the IPSLA will start sending probes and accumulating statistics. The next scheduling parameter will be the lifetime. It will set how long the IPSLA stays in operation. After it expires, no more probes are sent. By default, it is 1 hour. We can change that in seconds or set it to forever. So that means the IPSLA will never stop. The next parameter will be the age out. This will establish how long will certain IPSLA statistics remain in memory after the IPSLA stopped. By default, the value is never. That means that statistics for IPSLAs will be kept in memory forever, and we can set it in seconds. We also have the parameter that is known as recurring. This will mean that we'll be repeating this scheduling for this IPSLA every day. By default, it is false, but we may enable it. This is the actual command in order to schedule an IPSLA. We can establish the start time, the lifetime, the age out, and whether it will be recurring or not. The final stage in an IPSLA operation will be viewing the statistics through the command line interface. We have several commands. For instance, we can see the aggregated statistics, which show IPSLA statistics aggregated, the snapshot history, which show IPSLA history, and distribution statistics with the command show IPSLA enhanced history distribution statistics. Probably the command that we are going to use most often will be show IPSLA statistics, and we are going to look after the return code. When it is okay, that means that the operation is considered to be successful. We are going to see that the number of successes increases with every OK return code. This refers to the last probe operation result. Now, if the response for a certain probe arrived after the threshold setting, we will see that the return code will become over threshold, and the output that says over threshold occurred will become through. If a packet didn't arrive on time or we didn't receive a packet response at all, then the return code will become timeout and the number of failures will increase by 1. Let's move on and start explaining what IP SLA operations we have available with Cisco, how to configure them, and how to verify them. There are several types of IP SLAs out there. These variants are officially known as IP SLA operations. Each one of these has a different purpose. These are the most important ones. There are several of them. If you want to verify what IP SLA operations are available in your device, you will need to execute this command. The first operation that we are going to talk about is the ICMP echo operation. We are not simulating any specific type of traffic. This is just a generic traffic simulation. We are going to send an ICMP echo packet to the destination and we are going to wait for an echo reply packet. We are going to evaluate reachability and we are going to measure round trip time with this operation. We don't need a responder and we are going to configure it with this command. We need to provide the destination IP address. This is our lab. We are going to configure all of our IP SLAs here. In this case, we're going to ping this destination device with ICMP echo. So let's configure that. So 100 and then ICMP echo to 10.1.1.4 and then we are going to schedule it. IP SLA schedule 100, start time now, lifetime forever. We can issue show IP SLA configuration 100 to see the settings and show IP SLA statistics 100 to see the return code for the latest operation. Next operation, UDP echo. With this operation, we are going to simulate a generic UDP application. We are also going to test whatever quality of service settings exist within the network. We are going to send a UDP probe to the destination. In this case, the destination must support the RFC 862 UDP echo in order to be able to build a response and send it back to the source using UDP as well. We are going to evaluate reachability and measure round trip time. The responder in this case is optional and recommended. We are going to use this command. In order to enable this operation, we will need to supply the destination IP address and destination port number. Okay, let's configure UDP echo. We are going to go first here, and this catalyst is 9000, IP SLA 101, UDP echo to 10.1.1.4, port 4000. Let's go to this device and configure it as a responder, show IP SLA responder. And then for UDP echo for our address 10.1.1.4, port 4000, we are going to be listening here. And now we are going to schedule it. IP SLA schedule 101, start time now, lifetime forever. So we show IP SLA statistics 101. This is the statistics for UDP echo. Next operation, ICMP jitter. We are not simulating any particular type of application in this case. We are going to send several probes in tandem, one after another, using ICMP type 13, and we are going to be expecting several responses with ICMP type 14. In order for this to work, the destination must support a full implementation of the ICMP RFC 792. We are going to calculate in this way the jitter, delayed packet loss, and out of sequence packet. We need to send several probes in tandem because we need to calculate several delays. We need several delays because we need to calculate the variance in delay in order to calculate the jitter. We don't need a responder, and in order for this to work, we need to have network time synchronization between these two devices, for instance using NTP, and the command will be this. We need to provide the IP destination address, and optionally how many packets are we going to send in tandem, at what interval, and what will be their data size. Okay, let's configure this. We're going to use 102 for this IPSLA 102, and we are going to do ICMP jitter to the destination device 10.1.1.4. We are going to leave everything as default, and we are going to schedule it. So IPSLA schedule 102, start time now, and lifetime forever. Okay, let me refresh that, and then we are going to do show IPSLA statistics 102, and we can see the return time jitter is started to get calculated. Latency is shown as 0. Let's see if we have our clock synchronized or not. So we don't have NTP in place, so probably that is an issue. So we can configure this as master just as a test. Let's say that this is the NTP master for this network, and then let's make this synchronize with the other device, MTP server 10.1.1.4, and then we'll have to wait until these two get synchronized. So once the clock is synchronized, let's issue show IPSLA. We can see that we have now a calculation for latency, because if the clock is not synchronized, it will show up as 0. Let's see, show IPSLA configuration 102 statistics. The next operation is UDP jitter. In this case, this operation is actually simulating real-time applications such as voice over IP, real-time video conferencing, IPTV, and so on. We are going to be calculating one-way jitter, delay, packet loss, out of sequence packets. In order for this to work, we are going to send several probes in tandem. We need to send several probes at each iteration because we need to calculate several delays. We need several delays because we need to calculate the difference in delay in order to calculate the jitter. In order for this to work, both devices must be time synchronized, for instance using NTP. Otherwise, some statistics will show up as 0 and we will need to use a responder. In order to configure this, we will use this command. We will need to provide the destination IP address, the destination port, and optionally how many packets are we going to send in tandem, at what interval, and with what size. Okay, let's configure UDP jitter. Remember that we have a responder. We are going to make use of the IPSLA control protocol. We are not going to configure the responder explicitly. However, we are going to use it. And the IPSLA protocol helps us doing that. So let's issue show IPSLA 103. It will be UDP jitter, IP address of the responder, port 5000. And let's schedule it. IPSLA schedule, start time now, live forever, and let's issue show IPSLA statistics 103, and we have latency, jitter, RTT. However, if we issue here show IPSLA responder, there is no port 5000 explicitly configured, but however it is working. So this will be actually IPSLA configuration 103 and statistics. Next operation will be path echo. With path echo, we are not actually simulating a specific application. However, we are going to gather per hop delay. We are going to send a trace route in order to find what are the intermediate nodes in order to reach a destination. And after finding them, we are going to send ICMP echoes, particularly to these nodes, in order to gather the per hop delay. We don't need a responder, and we will use this command path echo and the IP address. However, in order to see this information, we will need to see the aggregated statistics. Okay, let's configure path echo. If we want to see what are the SLAs that we have already configured, we can issue show IP SLA summaries. So let's configure path echo. We are going to use 104 and we are going to issue path echo. Let's do a trace route to one of our application servers, in this case this one, and let's schedule it. IP SLA schedule 104, start time now, live forever. And then we are going to issue show IP SLA statistics 104. We don't see the statistics per hop here, and in order to see the statistics, we will need to see show IP SLA statistics aggregated 104 details for each hop. Now we can filter it. Let's include here a hop and the word hop and the word latency. So for hop 1, this will be the delay. For hop 2, this will be the delay. For hop 3, this will be the delay. And for hop 4, this will be the delay. Next operation will be PATH-JITTER. With PATH-JITTER, we are actually not simulating a particular application. However, we are going to send a trace route in order to find out what are the intermediate devices in order to reach this destination device. And after that, we are going to send several probes in tandem to every single hop in the path in order to calculate several delays. And when having several delays to reach each hop, we will be able to calculate jitter, because the jitter is the variance in delay. So we can calculate per hop in one way, jitter, delay, packet lost, and out of sequence packet. We don't require a responder in this case. In order to configure it, we will use the command PATH-JITTER. We will need to configure the destination IP address, and optionally how many probes are we going to send in tandem, and the interval and the data size. We can change that. Okay, let's configure PATH-JITTER. Let's issue first IP SLA 105 and then PATH-JITTER. Let's use the IP address of my DHCP server, for instance this one, and then let's schedule it. IP SLA schedule, start time now, lifetime forever, and then let's issue show IP SLA statistics 105. We need to wait a little, and then we are going to see per hop. Per hop, we are going to see the round trip time, the jitter, and packet loss, and out of sequence packets. So this is the next hop, the next hop, and the last hop. The next operation will be TCP-CONNECT. In this case, we are trying to simulate in a general manner how a TCP connection will behave from one part of the network to another. In this case, we require a responder optionally, but it is recommended to use a responder. So we are going to send a TCP connection. We are going to start up a TCP connection with the typical three-way handshake, and we are going to measure the time in order to set it up. In order to use it, we are going to use the command TCP-CONNECT, the destination IP address, and the destination port. Okay, let's do a TCP-CONNECT to the responder. So let's configure IP SLA 106, TCP-CONNECT to 10.1.1.4, and let's say the port will be 6000, let's schedule it, and so let's issue show IPSLA schedule 106, and then live forever, and start time now. So let's issue show IPSLA statistics 106, and we have the return trip time in order to set up a TCP connection to the responder. Next operation, HTTP. In this case, the IPSLA operation is going to behave like an HTTP client downloading a URL resource from a web server. In this case, several statistics are going to be gathered, because first we are going to query the DNS server in order to gather the IP address of the web server. Then we are going to establish a TCP connection, and then we are going to download a file through HTTP. So we can gather the DNS lookup time, the TCP connection time, the HTTP transaction time, and then we can summarize all of these times into a total HTTP time. So in order to do so, we are going to use these commands. We have several options here. We have the normal regular HTTP IPSLA with the command HTTP. We can use raw HTTP commands with the operation HTTP raw, and we can also use secure HTTP with HTTP secure. Okay, let's do a lab for the HTTP operation. We already have this server. We have this resource index.html available on this HTTP server with this IP address. So let's configure that. Let's go for IPSLA 107 HTTP get, and the URL will be this. We are going to use an IP address, so we are not going to query the DNS server in this case. So the statistics for the DNS query will be 0, and we can use the name server IP address here. However, when we are using an IP address, we will not need a DNS server. So let's schedule it with IPSLA schedule 107, start type now, live forever, show IPSLA statistics. We're going to have to wait because given this is a simulation, downloading an HTTP file is usually going to take some time. After waiting some time, we can see that we have one success, one failure. The DNS calculation is 0 because we are not using DNS server in this case. We have a TCP connection time and an HTTP transaction time, and we have a total. The next operation is FTP. In this case, the IPSLA behaves as an FTP client downloading a file. So we can calculate the download time. In order to configure this, we will use this command FTP, the URL, and we can choose to use active or passive mode for FTP. So for the FTP lab, we already have an FTP server. We are using this username, and we have this text here, whatever that text. We are going to use this text for our operation. So let's configure that here. It will be IPSLA 108 FTP get, and we are going to establish the username here, FTP user. The password for this user is this one, and then the IP address of the FTP server is this one, and the resource is whatever dot text. Let's schedule it with IPSLA schedule 108, start time now, live forever. So let's issue show IPSLA statistics 108. So this is the time that it took us to download this file. The next operation is DHCP, where the IPSLA is going to behave as a DHCP client. It is going to acquire an IP address, and then it is going to release it, exchanging the usual DHCP packets, discover, offer, request, and acknowledge. We are going to gather what is the time that we take in order to acquire an IP address. In order to configure this, we are going to use this command. We need to supply the IP address of the DHCP server. And there is an important detail here. The source IP address in this case matters, because this source IP address is going to be the relay agent IP that the DHCP server is going to use in order to match one of its DHCP pools. It is actually an IP address that lives here in the local area network of our router. Otherwise, we are not going to acquire an IP address from the DHCP server. Okay, let's configure the DHCP IPSLA. We have a DHCP server already in place. It is serving this pool. Within this device, we have an IP address that is living in this pool. So this is the default gateway for this local area network. So we're going to use that. Let's configure IPSLA 109 DHCP and the address of the DHCP server. And then the source IP address is important because it is going to become the relay agent IP. It is going to be this one. And then we are going to schedule it with IPSLA schedule 109, start type now, and lifetime forever. So we are going to have to wait a bit until this shows some results. So we already have one success with this. This will be the time that we use in order to gather an IP address, in order to acquire an IP address. Given this is a simulation, times usually can be high. The next operation is the DNS operation, where the IPSLA is going to behave as a DNS client, where it is going to query a DNS server. We are going to query a DNS server and calculate how much time the DNS server takes in order to resolve name query. In this case, we are going to use this command. We are going to provide a host name and the IP address of the DNS server that is going to perform the name resolution. So let's configure a DNS operation. Let's go for IPSLA 110, in this case DNS, and we are going to query, for instance, yahoo.com, and my name server lives in this address. So let's schedule it. 110, start time now, lifetime forever, and then let's issue show IPSLA statistics 100. So this is the time that my DNS server that is taking in order to perform name resolution. There are many others IPSLA operations that we are not going to talk about here. Many of them are used by service provider networks, not really suited most of the time for enterprise networks. For instance, MPLS or Ethernet over MPLS probes. Just a final note, within Cisco devices, we can create something that is known as an object, where this object have two states, up and down. We can link the state of an object with the result of an IPSLA. We have two options there, using the SLA reachability result or the SLA status. So for instance, if we were to use the status, timeouts will make the object go down, and OK will make the object to go up. Or if we were using reachability, reachable destination will make the object to go up, and unreachable destination will make the object to go down. As these IPSLA states can change rapidly, we need to avoid having the object states changes rapidly as well. We need to avoid that. So in order to avoid having the states of objects going up and down, we are going to use timers. So the IPSLA state should remain in the same state for a given amount of time given by this timer in order to become a valid state, in order to make the object state change.